Hello and welcome to SimScale webinar on cleanroom designs. My name is Paweł Sosnowski and I will have the pleasure of being your host today. Just a brief check before we roll into the thing. I would like to make sure that we all can hear each other and you can see my screen. It would be great if you would raise your hands right now using the GoToWebinar panel. I see some first hands rising up. That's very good. Thank you very much. I'll assume that this is true for all of you. And before we move in, I also would like to give you a short introduction, like what the general scope will be that we'll be talking during the presentation. If you have any questions, feel free to post them as we go. I will try to answer the fast and obvious ones immediately. If there is something heavier, we'll leave it for the very end during the Q&A session. Okay, let's jump in to the cleanroom designs with SimScale. We'll first have a short introduction to SimScale in general. Some of you might have only just heard of us, and I would like to make it a little more crisp who we are, what we do, and how do we do that. After that, we'll have a very brief and general description of how to approach cleanroom simulation projects, followed by a CAD preparation discussion with the presentation on how to do it on Onshape, one of our partners, the online CAD design tool. And this will be combined with the presentation of a simulation setup and the way to post-process result data on SimScale platform. As I already mentioned, we'll close up with a Q&A session, so if you have any questions, even during the presentation, do not hesitate to try to post them as we go, but if there is something more complex, please leave it for the end Q&A part. Let's begin with an introduction to SimScale platform. We are the first completely cloud-based engineering simulation solution that provides you with all the functionalities and all the possibilities of a modern, advanced simulation setup tool. There are no extra hardware required, no fixed cost, or even the training overhead is being significantly reduced thanks to moving all of those things into the cloud. We provide a workflow and a tool that requires only a CAD as an input, and later all the simulation design process from meshing, pre-processing, simulation setup and running up to post-processing and taking engineering decisions can be done through one of your web browsers that you choose to use. This is a great breakthrough, allowing you to have bringing down three barriers that so far blocked. First of all, we are becoming accessible. No more requirement of getting a huge supercomputer under your desk, paying extra money for maintaining it, upgrading it, setting up the things. You can do what you really want to. That is, make your products better. SimScale is cost efficient. We come at a fraction. The professional accounts come at a fraction of the price that our competition goes for. But most importantly, when you want to start simulating with SimScale, you can jump in and do it completely for free. The only thing we want to do to get from you in exchange is your knowledge. That is, sharing the things with the community. And this brings us to the third aspect of SimScale that is completely revolutionary. We are sharing knowledge between each other, thus providing the know-how to people who do not have so much experience with simulation, allowing them to jump and make simulations immediately or after a very short onboarding process, and getting the results, improving their products, and making our world better. We provide, as I already mentioned, we provide a full range of access to different types of analysis, starting from solid mechanics, fluid dynamics, thermodynamics, acoustics, particle phenomenon, and so on and so forth. Today, we'll be focusing mostly on the fluid dynamic aspect and particle tracking within clean rooms, so closed environments, and the possibilities. So that was the very short introduction. I know that most of you are here for this topic, and some of you already heard about SimScale, so I'm very glad that we managed to go through the 5 minutes of introduction. Let's jump immediately to the approach to the cleanroom projects and the way to perform them using SimScale platform and making simulations in general of such complex systems. The first and the most important step is the right definition of the scope of analysis that we are trying to go for. A crisp meaning that we are trying to look for the target goals, the limitations, and the required steps that are to be taken. This comes also with the amount of simplifications we are ready to take in order to properly be able to solve the complex phenomenon of the complete room. It might be that it is enough for us to take a look at a small portion of the whole phenomenon that is going on, like seeing the particles being moved or a passive scalar that is being distributed. It might be not required to take a look at the temperature behavior or buoyancy effects, which will be not significant enough to change the flow within the room. Any kind of simplification that we are making at this point, when we decide on the scope of analysis and the maximum requirement that we want to have, will provide us with faster results and more reliable results, since additional complexity will make it harder to detect any kind of problems that we may face. Let's take a look at the possible analysis focuses that we will be taking when dealing with clean rooms. We can try to look for a general airflow within the room that we are trying to see, without any extras added on top of it. We could try to locate the recirculation zones, which would indicate places where dust or other particles might be located and that will not be cleaned during the operation. This is what we're trying to avoid, and the design of the room and improvement of the design will focus on trying to removing this kind of recirculation zones from the room itself. Changing the airflow while modifying inflow and outflow conditions. Very often we will be facing situations when a single room will be operating under different conditions. We can have a laminar chamber. This is exactly what we'll be talking about today. We can have a chamber, reaction chamber, that will have a blower or a suction or a laminar chamber that is providing access to different tools. Changing the flow conditions and airflow conditions might be significant, especially also for taking a look at possible hazardous condition when one of the fans is malfunctioning, and we would like to see whether this poses some kind of a threat for people who are operating within a room itself. The air exchange and the time that it takes to completely clean the room is another aspect. Taking a look at the residual gas, dust, or particle tracking that is present in the room, or thermal behavior of the system, where we want to keep the constant temperature within the reaction chambers or within the clean room itself in order to provide optimal conditions for operation of this delicate equipment that we are working with. That was the general scope. Let's try to narrow it down and try to see what kind of modeling steps can we take. First of all, whatever approach we're going for, we'll need to take step-by-step approach to modeling this kind of complexity. We'll start with the simple flows, even a laminar flow within the domain, meaning that we're completely ignoring the presence of turbulence. We're using an incompressible gas with an inlet and an outlet. This kind of analysis will also give us an insight on the way that air is moving within the domain. After that, we can start adding passive scalars. This is a minimal overhead over the standard additional simple turbulent flow, and will immediately provide us with information on how is the air changing, where are the gases located, and how are they propagating throughout the domain. When this is done, we can move to improving or increasing complexity, like adding buoyancy terms and the heat transfer into the problem, or checking particle analysis to track where are they going. When moving with these steps, we should always evaluate the results that we're getting at each one of them. It might happen that, and it very often happens, that the results you already get with a simple analysis will be just what you're looking for and be enough to provide an insightful engineering decision on improving the design of your clean room. Let's talk a little bit about the simulation focus and the way to prepare a CAD for a clean room design. Because very often what happens is that we are tempted to take the design that we have, the engineering design or the building design that we have, and directly plug it into the simulation, press a button and say go. Unfortunately, this approach might cause us a lot of trouble. We are trying with simulations to make a modeling of the general room itself. And the first step that we should take is to remove the unnecessary features that are present within the domain. All the door handles, or the cables, or the little knobs and chamfers, the things that will not have a significant influence on the overall performance of the room need to be taken apart. I have to say that unfortunately very often this might even require us to simply build a mock-up of the general clean room design from scratch. But hopefully you will be able to directly make a volume extraction of your geometry, taking the part, cleaning it up, and then uploading it directly to the platform in order to make the simulation. And once more, I cannot stress how important it is to have this kind of defeaturing removed. If this is not done, if we are really sticking to making all these little details, first of all, we'll experience bad mesh quality around these elements, since the solver or the mesher will try to resolve the case and resolve the element itself. By doing that, it might, for example, ignore it, since it's very small, but very often it will still leave a bump or a little discontinuity of the mesh at the place where it was located. Later, during the analysis, this kind of irregularity of the mesh might cause problems for convergence or even running the whole thing. The second thing when it comes to cleaning up the process is that even if we have those little features and we try to resolve the mesh in order to represent them, this will increase the size of the mesh itself. What it means is that we get a better precision of the solution around the door handle. Do we really need a good resolution of the mesh near a door handle? I don't think so. We'll be more interested in a good mesh resolution or a good representation of the flow next to an inflow, next to the chamber itself, next to the reagents and parts where we have inlets of the inlets, the outlets, the reaction elements. That is the focus, not the little elements, knobs and small things. We should simply clean them up. The second thing is the proper preparation of the area of interest for the flow. Another thing that we usually do is simply define this is the open door that we have. For some reason we want to see what happens. We have an inlet that is a fan. We say this is the face of the fan. There is an outlet. Let's cut it immediately at the level of the floor. This approach is possible and very often will work. Unfortunately, it brings together with it some dangers for the stability of the system itself while it is being simulated. Why is that? Well, let's take a look first at the inlet sections when we are trying to where we are introducing the flow into the domain. Most of the time, the inlets will be presented with a single uniform velocity, meaning that everywhere at the wall or everywhere at the face, which is an inlet, the velocity will be exactly the same. This unphysical and not realistic modelization of an inlet will be directly inserted into the flow area of interest, thus reducing the actual and proper flow that should be happening within the flow of interest. For this reason, the first thing we should do is always extend the inlet area a little bit. It doesn't have to be much, but it would be good that within the extension, the flow will have the place to develop a profile that is actually representing the flow that exits the problem, that exits or the inlet section and enters the flow area of interest. It is especially important when we are talking about big sections of ventilation systems and when our inlet is happening exactly after some kind of a knob or an angle. An angle, like any kind of angle that is positioned within a flow like this, will create a different inlet profile and should be included within our model to properly represent the way air enters our domain. The second consideration regards the outlets themselves. We are very often tempted to directly position the outlets, or so-called open boundaries, immediately at the place where the geometry ends. At the same time, we should remember that the flow itself will have different features happening at various places of the flow, and very often this kind of recirculations might occur close to an exit section of our geometry. Let's imagine the case that we have here, that we for some reason would like to shorten up the geometry, and we were only interested in a certain close section to the jump that we have. The simulation itself does not understand what is going on the outside. It doesn't know that it should gently turn back and get into the flow with a nice parabolic profile or any other velocity field. It doesn't know what happens outside. Our job is to make sure that the flow has enough space to develop features that it's having, like recirculations, and that the outlets really perform the function that they are supposed to be doing. That is, taking the flow away, not introducing the flow into the domain. So we are extending outlets. Both of those actions will mean that we are making the domain bigger, and we are creating additional, not physically correct extensions to the inlets and outlets. But that is okay. Since we are introducing a proper flow into the area of interest, that's the first thing, and we will disregard any phenomenon that is happening after our actual outlet or actual limit of the flow. Finally, we need to consider what's going on within the domain and the physics that is going on. Let's say that we would like to model a filling of a tank, or in some cases, let's say we are putting a cleaning gas into a clean room. At the very beginning, there is nothing in the tank. Is it? In fact, we are having air inside, and when we'll start pushing anything into the domain, we will need to remove the remaining air from it. That's why we should consider always putting an outlet that will allow the residual part to move away. Let's take a look at an example analysis project that we'll be talking about, and so enough of the theory, and we'll move to the practical example that I have prepared for you. In this case, we will try to make a comparison of ventilation performance for a multi-purpose chamber in a small clean room looking like this. First, we'll go to talk about the CAD design and the way to prepare it on Onshape, and after that, we will move to the simulation itself. So the first focus will be to simulate the distribution of the reaction gases. Let's go back for a second. We see that there is a reaction chamber. There are some elements, some tubes, a pot, some kind of a box, and within them there will be reactions happening. Let's imagine that these pots will create gases that will be introduced into the system, and they could be some kind of toxic gases, which might be posing some kind of danger to the operator. In this case, we have the three operation conditions. We'll switch off the hood and the fan that is positioned at the top of the reaction chamber. We'll operate the chamber in a laminar way, trying to blow out all the contaminants and the additional reaction resulting reaction agents. And finally, we'll take a look at different suction chamber conditions, trying to estimate what should be the minimum speed of operation for our chamber in order to not pose any threat to our operator. In order to do that, we'll go with the first step that we discussed, talking about the model that we'll apply. And in this case, we'll go for a steady state simulation. We want to see what happens when the operation is continuous, when it's taking several minutes or hours of operation for the reaction to take place. At the very beginning, we'll go with a laminar flow simulation. This is a simple model, and it would be okay to start with it in order to get the first understanding of what's going on. On top of that, we'll immediately add passive scalar transportation, when we'll denote with 0 the clean air, and with 1 it will be the reaction, the 100% concentration of the reaction gas in air that is being transported. With the passive scalar transport model, we'll immediately assume that the gas itself does not have effects on the air itself. It cannot, it is not making it heavier, it is not creating additional buoyancy effects, it is simply being transported as it was, for example, increased amount of CO2 or anything else. All right, that was the preparation part, and we will move now to the design and CAD preparation demo, followed by the simulation process demo. I've already loaded the case in Onshape. To those of you who have already been using this tool, I'll simply walk you through the steps that I've taken in order to prepare this geometry. At the same time, I will not spend much time showing exactly how did I make the geometry, what kind of extensions were done. We'll simply try to get a step-by-step approach and see where did we end up and how did we end up in several steps. The first thing that I did was to prepare a general sketch of the floor and the main geometry of the element that we're trying to move. After that, making several extrudes allowed me to create the bulk of the domain. With that, we are ready to make some additional sketches, like extending the outlet. This would be enough to have the outlet set if I were to create this particular face that I am marking right now. But obviously, as we already said, it is good to extend the outlet in order to avoid some kind of recirculations that might be happening next to it. And this is exactly what we've done. We extended the outlet just a little bit. It is hard to say. I mean, this is just an example case. It might be advisable to extend it a little further, but for this purposes, we keep it as it is. Let's move on. The next thing was to create the how to call it, the furniture itself, let's say like this, by simply making a sketch and extruding it one by one. Further, we started creating the reaction chamber, making the bulk element, creating additional sketches and planes, lofts to build the reaction chamber. Again, this is simply a representation of the element. We have the first representation done, and following that, we are also adding additional features like the plates and the floor, the overhead floor on which the person or the scientist is moving. So we have the plates. The plates are now multiplied. There we are, with nice representation. It is quite important to remember that simulations will require us to sometimes overextend the sizes of the elements. I know that in most cases, these kind of floor plates will have much smaller thicknesses. But in order for the measure to capture their presence, it is required to give them some kind of a little more significant thickness. So we're doing just that. At the same time, even though we're performing this kind of action, it should not and it will not have a big impact on the overall performance of the whole domain, since it's much bigger than this element. Finally, we are finishing up several steps that we haven't done so far. So introducing top inlets that will be introducing only the fresh air. We are separating the outlet face, because before this step we had the whole top face to be selected as a single entity, and it needs to be directly split so that later the solver and the SimScale platform can recognize that this element over here is an outlet. And the last but not least, well, we forgot about the window shield that is present on the top, so I'm adding this element right now. And again, I'm over-exaggerating the thickness of this element just to make a general representation of what's going on. Okay, we have the room ready, and now it would be good to prepare some kind of lab equipment that will be working on this kind of room. So I did it in a separate tab where these lab elements were created. We have a little box. I mean, these are simple shapes that represent some kind of tubes and reactants where they can happen. So we have those parts and we are ready to create an assembly. The great thing with using an assembly method is that we can position different types of equipment inside our chamber and play with the positions with relative ease. So this is what I can do right now. I could capture this little guy here and try to, if I put a proper connector mates, we can move it around the plane and position it anywhere on the table. Let's try to move this part. It can go a little further back. The downside of this this approach is that, well, whenever we make modifications to the geometry itself, well, we will have to remesh the geometry, since it is making the modification. The modification is being made, and whenever we move something, we need to remesh it and rerun the whole simulation. But with the general setup that we've done before, we can do that with a relative ease and pretty fast. So geometry is ready. We have the assembly set. We can go to SimScale platform and start simulating. I've already uploaded the geometry to SimScale, so it is already here. We have the geometry set and uploaded to the platform, ready for meshing. I will not go directly into details of the way that the mesh was created. We will simply talk about the possible refinements that may be helpful in order to get a better performance of our simulation. First of all, we will need to make sure that all the features of the flow are properly resolved. So every line that is present in this CAD will get additional level of refinement, splitting the base mesh that is being created and the very coarse mesh into two. Further, we'll give more refinements and quite a lot of levels, like 4 times more refinements to these little faces. We need to have a sufficiently fine mesh in order for the flow to go through those openings in the floor. The thing is that whenever you have an opening like that, you should make sure that there are at least 6 cells in within the shortest distance. And this is the absolute bare minimum. Without that, the flow will not be able to be created and will not be able to perform in a good way. The simulation may simply break. Whenever I think of a mesh for those small details, I remember the picture of Mona Lisa. If I put this picture in the resolution of 32 pixels by 32 pixels, obviously I will not see any of the details. Sometimes we could use a bigger pixel to represent a big chunk of the same color of a painting. But at the same time, when we are talking about small elements, we need a finer resolution. And that's exactly what we are doing when increasing the mesh quality at those faces. The next thing is the chamber itself. Since the mesh is very coarse in the bulk of the flow, because we don't need to have a very precise behavior, I mean, we need a relatively precise behavior, but we want it to perform a little better around the chamber, we are giving some refinements to the chamber itself so that the faces it has will get a good mesh. The lab equipment is not less important. It is even, that is why it's getting, again, some surface refinements with even bigger levels of improvement. The table and the shelf, well, we want to have a nice representation of it, and it might happen that the basic mesh split that we have will not provide it, so we're giving 1 or 2 levels of refinement to it. Finally, the floor and the tiles, the in and out frames. This is to ensure that we have a good resolution next to the walls when the flow, where the flow will be going in and out. And finally, we created the most important part of this whole flow region is the chamber itself. This is why we created some additional Cartesian boxes, some virtual boxes that I'm trying to show right now. There they are. Let's hide this face also. So here we have the 3 Cartesian boxes that will define the inside region of the chamber, where we'll add additional level of refinement to have a better mesh quality and thus get a better representation of the flow that is going in there. The resulted mesh will look something like this. We end up having around 5 million elements, which is already a pretty significant mesh design. Notice the mesh, the overall mesh quality in the bulk of the flow. It is reasonably good, but it's not giving a perfect representation of every little detail. At the same time, we are getting the refinements next to the walls and next to the elements themselves, and the refinements continue when we are getting close to the areas of interest, like the lab equipment from which the contaminants will arrive, and even more next to the tiles themselves. We have at least, I think it's around 8 elements within the thickness, which will be sufficient to provide the flow, provide the outflow from the main region to the bottom chamber below the room. One more thing to point out is that right now we have what's called the volume extract of the room. It is like we would fill it in with some kind of molten metal and took away all the parts. This is only the air domain. There are no solid objects. There are possibilities of running conjugated heat transfer where we're also seeing temperature differences within the solids, but this is another level of complexity and should be only done after we have tested this initial configuration that we have here. All right. With the mesh ready, we're ready to move on to the next step of SimScale process, that is jumping from the mesh creator on the top view to the simulation designer and create your own simulation. I've already done several analyses for different rooms. We'll go and take a look at simulation creation. I'll create one more simulation just as a mock-up to show you what are the steps that are the first steps that need to be taken. Because whenever you create a new simulation, there's nothing there. You end up choosing the analysis type. SimScale provides you the possibility of running any analysis type from solid mechanics, fluid mechanics, as we already discussed. In this case, we will choose the fluid dynamic passive scalar transportation. It is possible to track more than one passive scalar. If we had different reagents in each of the lab equipment, we could say I want to track up to 5 different passive scalars, or 5 different reagents, 5 different trackers within the flow. They will not be interacting with each other, but at the same time, if we figure out where 2 of those are gathering and where their concentrations are above certain limits that we set, we could expect that this will be a place where some kind of reactions are happening, like where we have a big concentration of oxygen and then some other reactant, some gas that could spontaneously combust. In this case, we'll consider that we have a single reactant. Its simple simulation, and we'll move to a steady state analysis since we want to see what's happening at the end of the whole operation process. With this done, I'm ready to click save and confirm my choice. Two things will happen after that. First of all the changes that I've done are saved on the platform, meaning that I can switch off the computer, I can travel to Brazil, US, China, anywhere that I can get an internet connection and start simulating from this point on. Second of all, we have a navigation tree appearing with a template for the simulation, where now we will simply go from top to the bottom of this tree, entering every property and setting up the simulation to run. So the first step would be to choose the analysis type, then go on setting geometry primitives and so on and so forth, choosing the model, adding materials and so on. So I will not be doing the setup right now. We'll simply guide ourselves through the setup for this analysis that I've already prepared. It's running on the same mesh. I set up first the turbulence Schmidt number, which will allow for a better mixing of our process, but since turbulence is switched off, this is a redundant parameter. At the same time, we're considering that there is a certain diffusion allowed for the species itself, meaning that Brownian motion and Brownian distribution of the species will happen even if the flow is not moving. Although in this case we expect that the flow will be convection driven, meaning that our fans and our blowers will be the ones that drive the flow. The material we'll use is air, and selecting different materials is extremely easy. You simply click on the library and decide what kind of gas are you interested in, or what kind of liquid are you interested in. On the other hand, if you have a particular one that is not represented in the library, the only thing you have to do is specify the parameters of your flow and give another name. So let's say air01, and we will put air01 to be our material. I will not save these changes. Let's move on. We start with initializing the conditions, and there is absolutely nothing to be done here. Since we are looking for a steady state simulation, this will be later modified itself. But now we go to the very important step, that is setting up the boundary condition. The first ones will be the general inlets that will provide a steady inflow of clean air. We are assuming that passive scalar equal to 0 is clean air, and they will be constantly blowing with 10 centimeters per second with flow and cleaning up the room. Then we'll add this toxic sources, as I call them, with a very slow and very small mass flow rate coming from, and I'll have to now switch the view mode to surfaces, and they will be coming from the tubes and the internal sides of the pots. So this is where the reactants are coming, and that they are, let's say, disrupting the cleanness of this room. Let's, for a moment, clear the selection. And we'll also hide the back side so it's easier to see any other selections that we're making. Next, we have the outlets, and in this particular case, we have only a single outlet. That is this face over here where the suction is being done. Sorry, there is no suction being done here. It is an open outlet that is allowed, and the air is allowed to go in and out through it. We could think of adding some kind of a suction outlet, and this will be done in a moment at the chamber itself. Let's go on. Rest, we will have quite a lot of walls, and all of them are simply stagnant walls with no particular condition. And finally, there is our reaction chamber top. So this little face over here, which denotes the place where we will be, which we will be modifying, and this will only changing the condition on this particular face. With that, we'll be able to reproduce different setups for the program. The first setup that we have here corresponds to a situation where we have a fixed velocity set at this wall. And with a fixed velocity equal to 0, that is simply a closed wall. And this is a closed setup. After that, we would go to set up the numerics. There is not much to be changed over here. And choose the simulation control, giving a properly long end time value to get a nice converged solution, and writing only several steps along the way, since it is not that important. We only want to see the final solution, which will be the most accurate representation or the closest approximation to the final solution that we want to have. Okay. With this ready, I am ready to make an imprint of my settings. I'll create a new run, and just for the sake of example, I'll give it a X, and this will be closed. The simulation creates an imprint that is ready for starting on the platform. I will not begin it right away, and I will jump to the chamber, this chimney face, and I'll start creating different conditions, like for example setting up minus 0.1 of meters per second velocity blowing towards the element. This will correspond to a setup where we have a laminar chamber that is trying to clear out all the species from the reaction chamber. Right-clicking on the simulation run, X, laminar. Note that the imprint that we created for the closed chamber did not change, and if I open the settings of this particular simulation, it is still closed wall. I'll go back and create a third one, for example putting 0.5 meters per second blow. Since this is going in a positive direction, this will be a suction of half meter per second coming through this face, which will obviously create a nice suction chamber that will take away all the contaminants from the system. And once more, I'm ready to create a new simulation. Suction. Why am I doing this? Why am I showing you that I'm creating 3 different simulations? Well, this is to demonstrate the power of SimScale platform, where you can run multiple simulations. Each one of them is running on 32 computational cores, and all of them can be operating at the same time without putting any load to your computer. After they are finished, you will simply get an email notification and you can start working on the analysis of the results. So I could go, click Start, jump to the second one, click Start, third one, click Start, and within a minute, since we are sending quite a lot of data to the servers, they will be calculating. And obviously, we will not wait for them to finish. It would take quite a bit of time. Even for the closed chamber, it took me around 3 hours to make the calculation itself. The mesh is rather big, but we have the results ready, and we will investigate several possible conditions. First, to look at the reference case where we have a closed chamber, then where we have the laminar chamber with the blow of 0.1 meters per second downwards into the domain, then the suction chamber with 0.1 meters per second, and increasing the velocity of suction in order to see what is the velocity required for cleaning up the whole room and ensuring that the people who are working within it are not exposed to the toxic gases. So the results, let's imagine that the results finished, and we can jump to the post-processing stage and load the results onto the screen. So there's quite a lot of simulations here. I'll close most of them. Here we have simulation 6, mesh number 3, and I'll find our closed chamber simulation. There it is. What I have to do is select the solution field for this closed chamber and wait for a second for the viewer to load. obviously, the bigger the data set, the longer we have to wait for the computer to process it. All of the operations are being done on the local servers, and later you will receive a streamed in live image of the data set. Very little graphical processing is done on your computer. At the same time, well, even with the computers that we have, it takes a little bit of time for data sets to load, especially when they are big. The benefit of that is that you don't have to download anything. These results have several gigabytes of size, so why would we want to have them on our computer when we don't know if they are really relevant or not? So this is an example result, and let's say that I will go and make a nice slice through this domain in order to take a look at the velocity profile and so on. Okay, we have a slice, but I'll also do one more thing. I will add this chamber to be visible so that we know where did we make this cut. Adding this kind of ghost body is extremely easy. The only thing you have to do is change the opacity, choose the type of the coloring that you want to do, and use the eye icon to enable visibility of the element. That's it. Let's make a little rotation to get closer to the cut itself. We'll take a slice, take a look at this slice, and visualize, for example, the velocity field in order to show where does the air flow. Over here, this is the magnitude of velocity, and we will rescale it to 0.3, let's say, to see the main elements where the flow is happening. And as expected, since we closed the chamber, most of the flow goes from the inlets, enters through the open boundaries at the bottom, and flows out. At the same time, there's quite a lot of recirculation going on within our reaction chamber, simply induced by the inlets coming from our pots. They have to exit somewhere, and they are driving the flow. Now we'll visualize the contaminants themselves. And we can see that, well, the whole chamber is basically completely filled with the contaminant, and it is being pushed out. Fortunately, it's being washed away and downwards towards the exit elements, the exit chamber. This kind of slice, for obvious reasons, is not fully representing what's going on, so I'll add another filter. That will be the threshold filter, which will visualize every cell that has a certain concentration of a particular scalar on the screen. So let's wait for it to appear. I'll make the setup, let's say 0.2 to 1. So we are trying to see every position where we have at least 20% concentration of the contaminant up to the maximum concentration of the contaminant within the clean room. Okay, let's do some cleanup of this visualization to see the thing clearly. I'll once again show the underlying geometry of the closed chamber, which will result in showing, well, this is where we have the contamination going on. So the whole chamber basically is filled with the contaminant, and then there is this, I would call it almost a waterfall of contaminant that is being sucked through the floor and later is being dissolved and still sucked out further away. Obviously, I will not go and start preparing every possible visualization. I prepared some screenshots. This shows the 30% concentration of the contaminant. We can take a look at the streamlines, trying to locate the recirculation regions that are present in the domain. Some other view from the scalar part of this closed domain, or the same cuts that we've been seeing here. And now to evaluate the different behaviors, first we will take a look at the laminar chamber. Sorry, this is the suction chamber that is working. The rotating part, so the scalars, and the cut. This signifies that if we put the suction with 0.1 meter per second, we might experience some exiting amounts of the gas, and this shows that this is not a sufficient suction to provide a safe operation for our scientists. So we go next, we see half meter per second, and right now the velocity fields look much better. It seems as the contaminants do not exit through the windshield. The velocity profile confirms that. Most of the velocity and most of the air is being sucked through the chamber itself. And if we take a look at the scalar itself, we see that all of the contaminants are being directly moved away from the operator. Some streamlines to visualize the way the flow goes. And the last setup is the very fast moving 1 meter per second suction at the chamber, the behavior of the gases themselves. And with this we have a very fast, this is again 30% concentration of the contaminant. It is being immediately distributed and sucked away. In this case we have up to 10% concentration. It's being taken away and provides a good operation conditions. Okay, that was a very brief and initial introduction of the possibilities of SimScale platform on running the operations for clean room designs. There is much more to be discussed, but obviously we do not have time to do that. I would be happy to answer any questions. We still have several minutes. So if you do have questions, I would please raise your hand and start typing. And we'll wait and try to answer those questions as they go. Okay, there's one question. Is it possible to make the reaction between the two passive scalars? Yes, it would be possible with some models, but right now it is not a functionality available on the platform. So as I already mentioned, in these cases, we would simply try to track the regions where we have overlying concentrations of these gases, and we would assume that if there is a certain concentration of one and the other, this is where we will have the reaction happening. But to have a direct transformation of one to a third party, that is not possible yet. The next question, what about particles? Can we put particles into the flow? Yes, this is a possibility, although at the very beginning, whenever dealing with particles within a flow simulation, I would highly encourage to go with a passive scalar approach. It is much faster and much easier to set up, and provides a very good representation of what's going on with the system itself. And I see there is just one more question. What about air exchange and calculating the time of the air exchange? Okay, yes. So I understand the question. Okay, so when we want to see how long does it take to take away a certain old air from a, let's say, a room that we had in the example. What we would start with in this case would be to initialize the whole domain with passive scalar equal to 1, and then blow the fresh air with a passive scalar equal to 0. That would be, or the other way around, it doesn't really matter. And we would, most importantly, run a transient simulation, when we would see the evolution in time of the whole field. Obviously, after some time, but this would be a longer simulation and a longer analysis, after running it for a few minutes, let's say, of simulation time, we would evaluate what is the concentration of the passive scalar at particular regions of the flow. And if the overall concentration of the scalar is below a threshold that we consider clean air, then we would say that we cleaned the whole room with, or we filled the whole room with fresh air. Okay, I hope that this answers all of these 3 questions that we had. If there are no more questions, I would like to greatly thank you for participating in SimScale training and this SimScale webinar on Cleanrooms. I hope that you found it useful. And on behalf of the whole SimScale team, I wish to, first of all, last of all, wish you Happy New Year. And we are looking forward to seeing you on the platform, simulating and working with the Cleanrooms. If you have any questions, direct them to our support or directly to me, to our account managers. We'll be very happy to help you. So once more, that's been Paweł Sosnowski, and I thank you for your attention. Have a great day. Until next time. Bye-bye.